me start a new notebook for this. Okay. Okay.
Ready?
Okay. So I'm ready, yeah.
All right, I'll admit everybody.
Hi, everybody.
Hey.
So I'm
Hey,
happy.
John.
Hello.
Hey. Oh, Jen Home is there. Look at that. You can also see my face, right?
Yeah.
Josh Green looking hard.
Typing away.
Okay. We are happy to have Antonio giving today's gauge theory virtual presentation. I'll turn off my mic and let him take it away.
Okay. Thank you very much for inviting me. So I will start talking about some motivational problems that led me that made me interested in these instanton groups. So and the motivation comes from a question of Nemeti about singularity theory. So singularity of a complex surface singularity, and so you start with a complex surface singularity. So, for example, you have like you can look at the equation like at the germ of the surface with the equation z squared equal to x cubed plus y to the 5, and I mean this is a surface, and in C3, and the partials all simultaneously vanish in the origins where you have an isolated singularity. And once you have a singularity, you can look for a resolution of it. So this is a smooth surface as twiddle together with the map that has the following two properties. So pi is an isomorph, is a biholomorphism away from the singularity. So it's in particular is a diffeomorphism with the image, and the counter image of the origin is an algebraic curve with possibly many irreducible components, and these are smooth curves with normal intersections, and this is what people call the exceptional divisor. Divisor of the resolution. And okay, so once you once you have this resolution, you can encode the combinatorics of the exceptional divisor in a graph gamma with vertices that has one vertex for every irreducible component of the exceptional divisor, and then you connect two vertices of this graph if the two corresponding curves intersect. Indeed, you can make sure that when the intersection is non-empty, is exactly 1 point by blowing up like the resolution if necessary. Okay, so if you look at the resolution of the singularity, so basically you're gonna I mean we are just interested in the germ of the singularity and of the surface about the singularity. So what is really interesting about S twiddle is a tubular neighborhood of the exceptional divisor. So somehow in S twiddle you're gonna see like all these curves, right, intersecting each other, and then we are interested like in a tubular neighborhood of this. Okay. So this is this is a smooth form manifold. I will denote by W gamma, and the boundary of this four manifold is a three manifold that I'm gonna call y gamma. So y gamma is gonna be the boundary. So this is what people usually call the link of the singularity. Okay. And Nemetis, I mean, this is kind of a trend in singularity theory. The question is, how is what analytic properties of the singularities can be read from the topology of the link? So this is like the motivating question. How the geometry of the singularity is related to the topology of the link. Okay, and so let me give you a very specific type of question that can motivate this type of to motivate this. For example, if you have once you have the resolution, you can look at the the sheaves, the sheaf of holomorphic functions over there, and this has and look at the first homology group of it. Okay, and then this has a dimension, and this number is what people call the geometric. What is called the geometric genus of the singularity. And a question is how can you read these numbers somehow from the topology of the link? And so let me quote a theorem proved by Nemeti a few years ago. So the theorem says that the singularity is rational, meaning that the geometric genus is 0, even only if the following condition, even though if the following are satisfied, and the following are indeed equivalent. And the first is y gamma is an Heger-Fleur space, and then y gamma as a co-orientable C0 tot foliation. Sorry, does not have a co-orientable, so I'm just gonna write tot foliation. And the third is the fundamental group of y gamma is not left orderable. Okay, so if you look at this theorem from the point of view of a topologist, this says that this L-space conjecture from Heger-Fleur homology is true for the link for the link of complex surface singularities. And note that this class of three manifold includes a lot of interesting three manifold like Briscoe spheres. So so this is the point of view of the low dimensional topologies. The point of view of the algebraic geometer is that well, somehow we succeeded in connecting through Heger-Fleur homology. We succeeded in connecting the geometry of the singularity, namely this geometry, the vanishing of the geometric genus, to a property of the fundamental group. So the question of Nemeti after he proved this was what's next? So can we obtain some characterization for the singularities with geometric genus 1 from the link and stuff like that? And well, the point is, this is not known, and maybe there is one can ask, is there a hierarchy of properties such that like the zero layer of this property is equivalent for about groups, such that the zero layer of this properties is like left orderability, and then there are other things, and these properties somehow encode the geometric trees in some form. So how would you attack such a problem? Well, you see, there is this the fundamental group, and then there is left orderability. So a very natural thing to do would be to study SL2R representations, because SL2R acts on the circle, and then if you are lucky, you can lift such a representation to the universal cover, and then you get an action on the real line, and then a non-trivial action of the fundamental group of a three-manifold on the real line yields a left ordering. So, okay, and then so somehow then you become interested in improving the existence of non-trivial representation of the fundamental group in SL2R. Okay, so one then may start thinking, okay, maybe I can do something very similar to what Kronemer and Mrówka did when they proved the property P, right? So you prove existence of non-trivial representation by proving that there is non-vanishing of certain gauge groups. So now, unfortunately, at the moment we don't have any gauge theory for SL2R that is a non-compact group. So somehow you can lower a little bit your ambition and search, like, I don't know, for non-trivial representation in SU2. Okay, and these are and these are connected. These are connected to the instanton picture. So to instanton Fleur homology. Okay, so now I'm not gonna give a talk about instanton Fleur homology since someone did it already before me, and so I'm just gonna say a few things about it, and then I'm gonna go state the theorem we proved in this project we had with Irving Dye and John Baldwin and Steven Sivet. So I mean, let me say just a few words about instanton Fleur homology. Okay, so I'm gonna be interested in the framed version. Okay, and this was introduced by Kronemer and Mrówka, and then it was further developed by Scaduto. Okay, in particular, we borrowed a bunch of things from the work of Chris. So you have a three-manifold. Okay, and inside it a multi-curve lambda. I'm gonna call the framing. Indeed, there is no, I mean, we are not interested. I mean, the multi-curve. I mean, this is not an invariant for links. I mean, but this is. I mean, the invariant in the end is just gonna depend on the mod 2 class of this guy. Okay, and okay, and using this construct, using this Chern-Simons functional and all the theory, like all this projectively flat connection, whatever there is, this whole story. I'm not gonna talk about. I mean, you get some groups, okay, that indeed are vector spaces. Okay, and this group have a Z2 grading, so you can split them as a direct sum of two smaller vector spaces. And in particular, we are going to be interested in the case when the decoration, like the framing is empty, can be particularly interested. This is what we simply denote by I sharp or Y. Okay, so I don't want to go through the theory of. I mean, I don't want to even sketch the construction of this group. What is important to keep in mind is that the generators of the chain group leading to this homology are representations. Indeed, are representations of the fundamental group of the complement. So they come from representation of the fundamental group of the complement in SU2 with the boundary condition that the meridians the meridians of the component of the multi-curve go to minus the identity and up to conjugation, up to SU2 conjugation. Okay. So this is where the representation comes. And so somehow, if you can prove the non-vanishing of these groups, then you are likely to prove that there exist some non-trivial representations. And okay, what I'm so this instanton Floer homology has many similarities. I mean, has many properties in common with Hegel-Floer homology. In particular, Scaduto proved that if you compute the Euler characteristic of I sharp, meaning the dimension of the even part minus the dimension of the odd part, then indeed you get exactly like in Hegel-Floer, you get H1 of the three manifold. So in what follow, I mean, I'm so with Z coefficient. So in what follow, I'm assuming that three manifolds are rational homology spheres. Okay, so I mean, we are just here Y is always going to be a rational homology sphere, and so this leads to the fact that the dimension of I sharp is bigger or equal than the cardinality of H1, and the equality here holds. The equality here holds when the equality holds, we say that Y is an L space, an instanton L space. Y is, this is a definition. Is an instanton L space. Okay. So, for example, one may ask, what's the connection in between the L spaces of this theory and the L spaces of Hegel-Floer homology? And the answer, conjecturally, is that they are the same. Indeed, Kramer and Mravka, I think, conjectured that the group I sharp is indeed the hat version of Hegel-Floer homology with complex coefficients. Okay. Okay. So these groups are kind of hard to compute, and what we did in our project with John and Erwin and Steven was to make some computations, and indeed it came out from our computation that this conjecture is true for a certain for the three manifolds we were interested in, and the three manifolds are the one coming from singularity theory. So what we proved is that theorem. So this is myself and Baldwin and Dye and Sivak, and okay, and we proved that the instanton group of the link of a complex surface singularity is isomorphic to the lattice cohomology of the graph, where this lattice cohomology thing, I'm going to go to it in a moment, with complex coefficients. So yeah, this is complex coefficients. Okay, that indeed is isomorphic for because of some work of Olvert and Szabo. And maybe I should also add Nemeti. Well, this is isomorphic to the instanton to the Hegel-Floer group tensor C. Okay, so this is what we prove. Assuming that gamma is in almost maybe I should write it for almost rational graph. Okay, so when indeed we are, so I said that we are assuming that three manifold are rational homology spheres in this. So when this happened, the singularity, the tree of the singularity, the graph of the singularity is a tree, and the irreducible component of the exceptional divisor turned out to be rational curves. Okay, is a rational tree, maybe. So it's a rational tree. Ah, what I'm doing. Okay, what happened here now? Yeah, okay. rational 3. Okay, I mean, almost rational, I'm going to abbreviate it by AR. So what do I mean by almost rational? Well, by almost rational, I mean that here you have the graph. And there is a vertex where you have a certain framing. And if you substitute the framing of this vertex with a very negative 1, then the graph is rational. Okay, and when I say the graph is rational, I mean that the singularity of the graph is rational. And this rationality can be indeed detected with an algorithm. And this algorithm was found by our team. So it's a pretty this is somehow a pretty old subject. But I mean, there are still a lot of interesting questions and totally unexplored. Okay, so this is what we do, and so now I should explain to you what's this lattice homology thing. And okay, so okay, so let me give you an introduction to lattice homology. Okay, so and okay, and so what's the situation here? So we have a graph gamma. So we start with a negative definite graph applying 3. So these are the trees that come when I say that the graph is negative definite, I mean that the 4 manifold associated to it is negative. Okay, and okay, and then we fix a characteristic vector in the intersection in the intersection form of the intersection form of the 4 manifold associated to gamma. And okay, and then so this is an overall choice I make. And okay, and then I can consider the homology the H2 of W gamma of the 4 manifold, and with Z coefficients. Okay, and this is just I mean, this is freely generated by the irreducible components of the exceptional divisor. And I can imagine this this homology to as sitting inside the real homology. And this is again R2 the number of vertices. And so and this way I realize an inclusion of one. Okay, so there are these identifications and these natural inclusions. Okay, so now starting from the characteristic, so every time I think to a vector in Z to the number of vertices, I indeed mean an homology class. And actually a pretty easy one to realize as a divisor inside the complex surface, the resolution of the singularity. Okay, so and then we for using the choice of the characteristic vector, we form this called Riemann-Roch function. And this is just -1/2 k evaluated on L plus the square of L in the intersection form of W gamma. And okay, so this is what I will call the Riemann-Roch. So the Riemann-Roch function. So this comes indeed from an application of, I mean, this is some sort of Euler characteristic of sheaves of sections, but I'm not gonna go through it because it's not interesting for us at the moment. And okay, and then using so now you see we have Z to the n sitting inside R to the n. So we can imagine the point of Z to the n as an integer, an integral lattice in R to the n. Okay. And this determines a subdivision of R to the n into cubes. Okay. And okay. So and indeed, like I say, I mean, and this I have to imagine a CW as a CW decomposition of R to the to the n. And now I can use the Riemann-Roch function to form a filtration of this R to the n with simplicial pieces, and the filtration is and this filtration contains, like, it has some pieces. Okay, and what are the pieces of the filtration? Well, this is m to the n is going to be the subcomplex spanned by the vertices with the Riemann-Roch weight less than n. Okay, so this is a filtration. Indeed, you can see that in the cases we are interested in the cases we are interested in when it comes from singularity theory. So the graph is a negative definite and whatever. So when you take n very small, then this is going to be very negative. This filtration is going to be empty. And if you take it very big, if you take n very big, then indeed you are going to get contractible subsets of R to the n. Okay, so okay, so now we have a filtration, and what can one do with the filtration? Well, many things. What we are going to do is we are going to consider the associated persistent homology module. So this is sum over n of the homologies of the pieces. Okay. And I'm going to use complex coefficients. Usually people here would put integer coefficients, but I'm going to use complex coefficients because we are interested in connecting this theory to the gauge groups. And note that this is a natural structure of a CU joint U module. Well, coming from the multiplication of U is the one induced by the maps, by the inclusions. Okay, so you sum up all the inclusion maps, and then you get an endomorphism on C star, and this generates a C joint U action. And okay, and indeed, so and I'm going to call the homology of this complex. I'm going to denote it by H star. Okay, so this is going to be the homology of C star. Okay, indeed, this group only depends on, depends from the choice of the characteristic vector, but characteristic vector inducing the same species structure on the boundary generate the same group. Okay, so I'm going to consider also the total lattice homology module, and this is going to be sum over k, where k spans all. I mean, with k you are spanning sum over k of H star. Okay. Gamma k, where I extend the sum over all over a complete set of representative of the species structures on the tree manifold. Okay, and well, the conjecture of Orgevat and Szabo and Nemeti is that indeed this homology is isomorphic to Egerfler homology. So here I'm using complex coefficients, so you should use also complex coefficients in Egerfler homology. More precisely, HF minus of Y gamma. Okay, and then the isomorphism shifts the grading somehow. And this I'm okay. And okay, indeed, this is true in some cases. For example, this is true for almost rational plumbings. Okay.
We don't see what you wrote. At least I don't.
Oh, that's.
I don't either.
Oh, okay. What happens now?
Nothing. Something weird.
Now.
Oh, now. Yeah.
Thanks, Gordon. Okay, so very good. So let's go.
Oh, can you return so we can see it?
Okay, yeah, so I said that the conjecture says that there is an isomorphism in between the lattice cohomology of the graph gamma and the HF minus of the link of the singularity. And indeed, this is true for almost rational plan. Okay, and this is what we are specialized in for this talk. Okay, so what's interesting about almost rational plumbings from the side of lattice cohomology is that almost rational plumbings have vanish. I mean, the high cohomologies of lattice cohomology vanish. So hi of gamma is 0 for I bigger or equal than 0. So what's really interesting in this for these guys is the h0 of gamma, and so this is the object of interest. Indeed, for our purposes, we are. I mean, this somehow corresponds to HF minus. So in our case, we are interested in HF hat. So what's the interesting part of this guy is the kernel of the multiplication of U inside here that I called I'm gonna call H gamma. Okay, so this group has a very explicit description I'm gonna give now. So okay, so how does it work? So this already appeared like in a paper of Oshbat and Szabo. So one consider the vector space, the infinite dimensional vector space generated by over C by all characteristic vectors. Okay, of the four manifold of associated of the plumbing. Okay, and so the elements in here I'm going to write as a formal linear combinations with complex coefficients. Okay, and the KIs are going to be characteristic. Okay, and so it turns out that H gamma is equal to V gamma quotient by the relations the following relations. So let me reorganize what I wrote. Okay, and what are the relations? Well, there are two type of relations. So the first one is if characteristic vectors can be evaluated over the vertices. Notice this, because the vertices of the plumbing graph are represented by spheres, represent spheres inside the four manifold, and then you can just evaluate the characteristic vector over there. So if K evaluates on a vertex with absolute value bigger than minus v squared for some vertex, then we say that we impose the relation 1 tensor K equivalent to 0. And then there is another one. If K evaluates, if a characteristic vector K evaluates over a vertex with to minus v squared for some v, then we impose the following relation. The generator associated to K is equivalent to minus 1 to the v squared tensor K plus twice the Poincare duo of the vertex V. Okay, very good. So this is an explicit description of the kernel of the multiplication by U. So are there any questions so far? Okay. Good. So okay. So what we prove is that, I mean, I stated the theorem in the beginning. I mean, what we prove is that this group here, H gamma, can be identified with the instanton, the framed instanton Floer group associated to the I mean, when you take the framing to be empty. Okay, okay, and how this proof goes, and well, so let me outline. Okay, so the proof is based on the existence of cobordism maps in instanton Floer homology that work basically like I mean, they have many similarities with the maps in the Heger-Floer setting, and suppose you have a cobordism. Like a framed cobordism in between two framed three manifolds. So a framed three manifold is again just a three manifold equipped with a multi-curve, and well, and the framed cobordism is just going to be a cobordism in between the two three manifolds containing a surface, an orientable surface interpolating in between the two framings, and these guys induce maps. And these maps I'm going to denote by F sharp X nu in between the respective I sharps. Okay, and furthermore, I mean, exactly like in Heger-Floer theory, one has an exact triangle. Okay, so this was there, like has been there for a while till this year, I think, or maybe last year. Baldwin and Sivek showed that these maps have a key property in common, like they share a key property with the Heger-Floer maps. Remember, in Heger-Floer homology, you always have these spin C structures going on. Well, here there is no spin C structure so far. Well, the point is that indeed you can force them in, and Baldwin and Sivek proved that the maps associated to cobordisms split along characteristic vectors. That somehow, I mean, if the cobordism is simply connected, you can think this as a species structures. Okay, so okay. Okay, and this splitting along spin C structure, I mean, that we can made of, I mean, in our case, I mean, our cobordisms are simply connected, so this is exactly like spin C structures, and so I'm gonna use the two terms interchanging them. So note that there is no spin C splitting of the groups on the boundary. So yeah, I mean, that's a thing to observe. Okay, so let me quote some properties of this splitting. So the first one is that F sharp in the map is zero. These maps are zero almost always. Case, and when I say almost all case, I mean all of them except a finite number. So all of them in the almost all of them in the counting measure, and then they satisfy two more properties, and one is the adjunction, and the other is the blow up. And yeah, let me state them. So the adjunction says that if you have non-vanishing of the maps, then a certain geometric property should be, is satisfied. So, and the geometric property is the adjunction inequality. So K evaluated on a surface plus the square of the surface in respect to the intersection 4 is less or equal than minus the characteristic, the other characteristic of sigma, where sigma is any smoothly embedded surface with the genus bigger or equal than 1 and positive self-intersection. Okay, so this is an important thing we use in the proof. And then the other key property we use is the blow up. And the blow up says that, well, suppose you have a cobordism, then you can always blow it up. And when I say you, I mean, these are framed cobordisms, so you blow it up away from the framing. And okay, and if I call E the exceptional divisor, then you know I can look at the map with the associated to the blow up cobordism that has the same hands and in the same decoration, and then I can take the species structure I had a certain species structure on X, and then I can deform it using the exceptional divisor. Well, it turns out that this map is not that different from the map associated to X. Namely, this is the old good map. I mean, the map we had before. If L is plus or minus 1, and 0 if otherwise L is not plus or minus 1. Okay, so these are the two, the adjunction and the blow up. Okay. So let me now outline the argument. So with this said, I can outline the argument we used to identify the two groups. And the idea is to build, I mean, we just build a map. And I mean, this construction is inspired by a similar construction that was performed by Alfieri and Szabo. And so the idea is the following. So you have the graph yields a 4 manifold, right? W gamma. Okay. And on the boundary of this 4 manifold, there is the 3 manifold Y gamma. Okay, so we are gonna okay, and now we can carve out a small like we can remove a small ball from W gamma, and now we get a cobordism between S3 and Y gamma. So it turns out that this cobordism as a natural can be equipped with a natural decoration, D gamma. So this is a properly embedded surface in Y gamma. In W gamma. That is what I call the natural decoration. Okay, so I'm not gonna describe this this surface explicitly, but I mean this is a key choice that somehow if you make this choice wrongly, then you know you get all sorts of problems with signs and stuff. So I mean this is somehow a big technical detail I'm omitting here. And okay, so this is the situation. So now I'm gonna define the map. And the idea is that one first defines it at the level of chains. I mean, at the level of the vector space phi gamma, and then one has to verify that the relations are satisfied. And because always remember that H gamma, right, is V gamma modulo some relations, and where V gamma is simply this free vector space generated by characteristic vectors. Okay, so and we build a map with values in the group in the instanton Floer group I sharp associated to Y gamma. And how you do it? Well, this is some sort of tautological maps. So first of all, you have to observe this thing that that this cobordism gives, I mean, equipped with the proper decoration gives and then with the characteristic vector gives a map in between I sharp of S3 and I sharp of Y gamma. Okay, and note that the instanton group of S3 is just a copy of the complex line, so we can fix a non-zero element in there, 1. Okay, so I'm gonna call it 1. You know, this is a vector space. The only distinguished element you have inside is 0, but you know you can fix another one, and I call it 1. Okay, so now how we define this map? Well, we can define it on the basis, and then we extend by linearity. And how do we express it on the basis? when, well, a generator is something like of the form 1 tensor K, and then we define it this way. We take the map associated to W gamma and D gamma, with decoration D gamma, and the characteristic vector basis element, we keep the coordinates with that. And then we can consider the associated coordinates map, and this is a map from I star of S3 to I star of Y gamma. So we can evaluate it on 1. And this is an element in the instanton homology. Okay, and so the proof, with this said, well, one has to prove 2 things. Well, the first is that this map descends on at the homology level and gives a map in between H gamma and I sharp, and it does. And so let me state this as a lemma. T sharp descends to a map on H gamma, and there is an important remark about this map, and takes value and takes values in the even part of the instanton group. Okay, so well, this is because this is I mean, these elements come from the coordinates map, right? And this homology, the homology of S3 is concentrated in degree 0, and if you use Scaduto has a formula to compute the degree shift of the coordinates map in instanton homology, and then when you apply that formula, well, you find out that the degree shift is 0, and so this map sends like even guys and even guys. So in the end, you just hit the even part. Okay, so what we prove is, and this is somehow the theorem. Maybe I use another color. Yeah, let me use, I don't know, green, orange. So, and the other theorem is well, that T sharp from H. Why did I here I? Yeah, okay. Okay, sorry about that. So in between H gamma to I sharp even, Y gamma is an isomorphism if gamma is almost rational. Okay, and okay, note that once you compute the even part, since I mean, these are just vector spaces, so the only information in the groups is the dimension. So once you compute the even part from H gamma, you can compute the dimension of the odd part by simply using the Euler characteristic business proved by Scaduto. So the difference of the dimension of this guy and the dimension of the odd guy you don't know how to compute, well, is equal to the cardinality of each one, and that you can compute. So because it's just the determinant of the intersection form. So so this is equal to a computation of this group, and the computation of this group can be hard. And indeed, I mean, recently there has been work about this by Juanita Pinzon and Ty Liedelman, I think. So this adds some more computations. So the proof of this theorem, I mean, how does it work? I mean, I can say a couple of words about this, and then I can say a couple of words about the lemma. So the proof of this thing is somehow the following. We prove, we establish a surgery exact triangle in lattice homology.
I don't see what you're writing.
Oh, again. Okay. So now we know the fix, right? Stop sharing. Share screen again. I add, here I play. Now what's going on here? Why this? No. So this never happened. Sorry about that. I don't know why this guy does not. Okay, there we go. Okay, sorry about that. I don't know why this happens sometimes. Maybe it's because I'm using the Bluetooth. I had to use the cable. Don't know. Okay, so the proof is we established a surgery exact triangle in lattice homology. That is natural with respect to T sharp, meaning that if you take the exact triangle in the analytic theory and the exact triangle we establish in the lattice homology setting, and then you take the T sharp maps in between the corresponding groups, then you get a commutative diagram with the top and bottom part of the diagram that are exact. And then somehow we can once you establish this, you can run an argument by induction. First, you start you prove it by induction for rational graphs, like by doing induction by blowing up like leaves, and then you can extend to one bird point case by taking by applying the exact triangle to a meridian of the bed vertex component. Anyway, I mean, this is once you have this is somehow this is the 5 lemma. Okay, so it's homological algebra, and I still have 2 minutes maybe, since we started 2 minutes later, and I mean, just let me say what how to what extent, I mean, how this lemma thing is, how you prove this lemma. Well, this lemma is basically, the proof goes as follow. I mean, it's based on the following remark. So here you have the cobordism in between S3 and Y gamma, and you see every vertex of the graph. You know, every vertex of the graph correspond to like a rational curve in the exceptional divisor. So it gives you a sphere. Okay. And then you can look at the tubular neighborhood of the sphere. Yeah. Okay. So you can maybe imagine that this ball, the ball we remove is inside here. How do you do this? Okay. So somehow you can imagine that the ball is in here, right? And okay, this is a disk bundle, right? And now you see you can in the end, how you define this map T sharp is by applying a cobordism map. Now the point is that this cobordism map factors through the map associated to this length space cobordisms, right? So if this map, if the length space map sends this map here, the length space map sends something to 0, then the big map also, like the composition does, right? And so this imposes some obvious, I mean, this imposes some obvious restriction on the kernel of the map T sharp when defined on the vector space V gamma. And basically, what we prove is that the relation, this relation come on V gamma, these relations here come from this decomposition of the cobordism. And so in the end, the proof of the lemma is a computation, is an explicit computation of the cobordism map of the length space cobordisms. So these are like the simplest one. So you have like like an a knot with framing minus b. And yeah, once you have you compute these maps, then you can prove that the relations are satisfied, and then you can go on with the 5 lemma, and that's it. So this is what I wanted to say. So we can do the German thing and knock on the table. Okay, so I don't know. Maybe someone has to say that for me. I mean, are there any questions?
Yeah, I have a question.
Yeah.
So the
Hi, Paolo first.
hi, the surgery excess sequence in lattice Floer homology didn't exist before.
So it existed. The point is that it's true. The point is that there was a sign issue. So somehow we need to define that. I mean, to have a very natural to prove the commutativity of the squares in a very natural way, we decided to change the exact sequence on the lattice side. So it's somehow like it's basically the old good one, but somehow we had to tweak it a little bit to make sure that there was commutativity of the diagram. Also, our definition of the relations of the group H gamma are slightly different, I think, from the one of Olschwert and Szabo, maybe. So there are some slight differences, but then it's the same.
I think another thing is that you have to define the map from lattice cohomology to the framed instanton homology.
Yeah.
You have to define that map, and so a big challenge is how do you define that map? To do that, you have to show that the cobordism maps in framed instanton homology satisfy the right relations.
Didn't you say at some point that a map on I sharp was factoring through H gamma? I forgot how that worked. I mean,
so the point is that you see, I mean, when you define T sharp, right? You use this cobordism maps, right? So but now this cobordism map here, for every time you have a vertex for every vertex of the graph, you can write this map as the composition of a map depending on the of the map associated to the length space cobordism. I don't know, I call it a BP, and a composition of like this is the first map you like just.
Yeah, are you writing something?
Yeah,
we don't see it.
You cannot see again.
Mm.
Okay. Stop mirroring. Mirroring again. Oh, okay. So now you should see. Okay. So so you have this cobordism map, you see, and then this you can write for every vertex yields a sphere, and the tubular, like you look at the tubular neighborhood, and then you can decompose this map as the composition of F sharp of VP, the cobordism associated to the sphere with self-intersection minus P, and then you apply it to 1, and then you apply the complement of the cobordism of the length space cobordism in here. And you see, if 1 is sent to 0 by this map, you see here there is a characteristic vector too. And if 1 is sent to 0 by this map, then is going to be sent by the composition to 0. So this is going to be 0, right? So this is what yields the relations. And the point is that you have to understand what this map sends to 0 to find the relations. So this leads to an explicit computation of the length space cobordism. And then we do. And the way we do is we go by induction on P, and we blow up, and we use adjunction.
Okay.
Unfortunately, I don't have time to show that.
Thank
But
you.
I mean, yeah, we can talk about it if you want to know the detail.
Does the tweak in the lattice Floer homology exact triangle then also carry over to how you would relate this to Hegardt-Floer?
Sorry, I didn't understand the question.
In the modification of the way things work in the lattice Floer homology side, do you have to do the same modification? Does the same modification then take place if you would try to use the same proof to show the equivalence with Hegardt-Floer homology?
So the proof of it's very similar to the one of Hegardt-Floer homology. So there is a complication that in the original proof of Olschwert and Szabo, they have there is. So the point is that in instanton Floer homology you don't have HF plus, okay? So and the original proof was using this the HF plus theory somehow, and then And then somehow we had to tweak a little bit the proof to make sure that we could do everything with HF hat. And this was like somehow the important thing. And then somehow the proof is just the same. I mean, there is this choice of the natural decoration that is very important. And but there are some small technicalities here and there, but somehow the real problem we had to overcome also was that the original the proof in the Egerfleur side was based on the existence of HF plus, and then you don't have like a theory with the multiplication with module structure here. So and indeed in the original paper of Zabo, they obtained like a slightly stronger result and than the one we got. Because they can extend somehow the proof a little bit to 2 bad points, and here we can just do 1. And this is the reason is that somehow we are doing we are handicapped by the inexistence of DHF plus. And but then the proof is the same. I mean, there are signs here and there, and you have to be very, very patient. But that's it. I mean, yeah. So I don't know if this answers what you asked.
Mm-hmm.
I have a question. So I# has a ZMod 4 grading. Can you compute that?
Oh, that's a very good question. That's what really. So the maps are not Z4 homogeneous, I think. I don't know. I mean, yeah, I think this is the reason. I mean, I wanted to have the Z4 grading, but then we had problems, and then I think the reason is that there is the maps are not Z4 homogeneous. So and you know, how would you define the grading on the combinatorial lattice cohomology? Well, you say, I mean, you just see the grading of the guy where I sent 2 by T sharp, right? And then you pull back the grading somehow. So you declare the grading of K to be the grading of his image through the map. And then you don't have the map is not homogeneous. You are screwed. You cannot play this game. And that's, I mean, how in the original Zabo paper they define the grading in lattice cohomology.
So when you say not homogeneous, it's with respect to this spin C decomposition?
Yeah, I think so.
Yeah. Like that. Okay.
Yeah, that's
and also just another kind of general question, is lattice cohomology defined only for plumbed lattices?
What do you mean by plumb? Like, what
I mean,
do you mean?
like if I take the Leach lattice, can I compute its lattice cohomology?
Say it again.
If I take the Leach lattice, can I compute its or make sense of lattice cohomology?
I don't know what's a Leach.
Yes, any lattice.
Just the lattice.
Any lattice. Oh, I see. Okay, so yeah, you can. The point is how this is related to Egerfleur. So one thing we have, I didn't mention at all, or to instanton Fleur. So what one can also do, and so the point is that how you think to a plumbing with the cycles. Okay. So one way is you do the plumbing construction. There is another. These graphs can also come from topology in another way. So you suppose you have a knot in S3. And you take a diagram, and then you have the Gerritz matrix, right? The Gerritz graph, right? The white graph, say. And then this graph, it's like a plumbing graph, right? And then you can build a 4-manifold associated to it. You can do it 2 ways, using the diagram, because the surgery diagram, right? Because this graph is embedded in the plane. So this graph yields like to a surgery like yields a surgery diagram. And this is a 4-manifold, and then this is the 4-manifold you want to think about. Okay, so if you think about this 4-manifold, then again you can run all these arguments, because this is a 4-manifold, and what's the boundary? Well, the boundary is the double branch cover of the knot. So now you can run the entire program I outlined here in the case of this cohort, the one coming from the Gerritz graphs. And when you run this thing, everything works fine. And so now rational graphs are substituted by almost alternating knots or alternating knots. Okay, say alternating knots. And what does it mean? One almost rational in this setting? Well, it means that in the diagram you can find you have a diagram of the knot in which there is a ball, and inside it you can see a braid. Huh? And this braid,
unfortunately, we can't see a braid.
You cannot see it again, yeah, because the guy forgets about me, and then stop mirroring. Okay. So I do something. Okay, there we go. So suppose, like, you know, you have the diagram, and then inside the diagram, maybe you can find a braid such that if you change all these crossings, you swap all these crossing, then you get an alternating diagram. Okay. So if you have a diagram of this type, this is not if you have just one crossing, this you have to change. These knots are called almost alternating. That is not the same as quasi-alternating. For a while, I thought, when I read the definition, I thought maybe they are not. These are called almost alternating. So you have basically, this is the most basic case. You have a knot diagram such that there is a crossing. You swap, you get an alternating diagram. Well, in that case, you can run this argument, and you can compute the I sharp of the double branch cover. And so this is an additional computation. Yeah, one can do with this method. I mean, we are writing up the paper right now, so we went through the like in detail with the plumbing story, but I think we can extend this to the Gates plumbing, and this somehow yields some more computations, and then yeah, because there is a lot. The group H gamma is defined for double branch covers. It's not defined for all diagrams, and I mean but you know, for when there is like almost alternating diagram, then you can run this thing. It was Chris that asked me this question, right? Okay, cool. Did I answer?
Yes, thanks.
Okay. Any more questions? There are a lot of P. Daniele Celoria, Marco Gomez. Look at this. Paolo Gigini. It was a while I didn't see Paolo Gigini.
So I think we can thank Antonio again for a wonderful talk. Next week, we'll have Peter Kronheimer speaking about Dane twists on the sum of K3s.
Surprising how these things are.
Yeah. Oh, yeah. Right.
Okay. Thank you for having me.
Thanks, Antonio.
Bye. So now they have to understand how to